Today's maths lesson, we're going to quickly just dive into the core maths and just remind ourselves the next section is one where it helps to make a substitution. So if we look here, we've got something squared minus 2 lots of something minus 3. We can see that this is basically a quadratic equation. If let's look at the specific example now below. If we were to multiply this out, we would get what we call a quartic, a power 4 equation, which would be very awkward to solve, actually beyond the scope of core maths. But if we were to make a substitution, we'd say, let's let this stuff be k. Let k, you don't have to use k. K is the most commonly used for these substitutions. We often call them k substitutions, all right? X squared minus x. So now we've actually got a different equation, and it's actually a simpler equation. It's actually k squared equals 8k minus 12. Right. We can now solve this. Okay, I'm not going to actually solve it, but I'm not going to show the working, but we get k equals 2 or 6. Don't forget, that's not the answers, all right? The question never had k's in it, it had x's in it. Now we need to solve x squared minus x equals 2 or x squared minus x equals 6. Right, and both of those are just standard quadratic equations, and we end up with 2 solutions here and another 2 here. All right. Try some of these questions from exercise 6 now, which runs over a couple of pages to page 18 and 19, all right? 17, 18, and 19. Okay, for now, though, we're going to dive back into the further studies. Just a quick reminder that tomorrow, in tomorrow's lesson, at the start of tomorrow's lesson, you need to hand in both of those tutorials. There's one for paper 1, so there's one for core maths, and there's one for further studies maths, one on blue paper, one on green paper. By all means, get help from one another, but please don't just copy someone's work. You're not going to learn anything by doing that. Back to this question that we finished off with yesterday. How many rectangles in this figure? Well, the thing that every rectangle will need is it will need 2 horizontal lines and 2 vertical lines. So, for example, if I choose those 2 horizontal lines and these 2 vertical lines, right? Then I've actually defined a rectangle in here. There it is. That's that particular rectangle. That's one of many, many rectangles in this diagram. So the question really is, how many ways could I choose 2 horizontal lines from the 1, 2, 3, 4? And the answer to that is just 4 choose 2. 4 choose 2 is 6. All right, and then I need to know how many ways can I choose vertical lines from 1, 2, 3, 4, 5, 6, 7. I need to choose 2 vertical lines from 7, and that is 21. Right, but with any one of these 6 combinations of vertical lines, of horizontal lines, these are horizontal, these are vertical, any one of the 6 horizontal combinations of 2 horizontal lines, I can have any one of the 21 vertical lines. So in fact, the total number of rectangles will be 6 times 21 or 21 times 6. It'll be 126. Really cool way of solving that problem. Let's just check with a much simpler example that method has actually worked. All right, here we've only got 3 vertical lines and I need to choose 2. And we've also got 3 horizontal lines and I need to choose 2. And when I multiply these 2 together, I actually get 9. All right, and in fact, there are 9 rectangles in this diagram. Let's count them together. The big one is 1. This little one here, 2, 3, 4, 5. All right, then and I'm going to shade these and count them. 6, that one going across there. 7, that one going across there. And 8, this one going here. And 9, this one over here. So it definitely works. Okay, we're moving on to section 3, right? And in section 3, we're going to start talking about probability distributions, all right? And it's a continuation of our study of statistics, but specifically probability distributions. The first thing we're going to talk about, though, is the difference between discrete and continuous variables. Discrete variables can only take on whole number values. In other words, our x values would be an element of the natural numbers, 1, 2, 3, 4, 5, 6, etc. Continuous variables, and so this would be things like number of children, all right? Continuous variables can take on the whole range of values. So this might be amount of tea in a cup. We could have 37 milliliters. We could have 355,48 milliliters. Here, the values are elements of the real number system. Right. The distinction between discrete and continuous has important considerations for speaking correct English. All right. This is incorrect. He scored an amazing amount of runs on the offside. We don't say amount when we can count them. When they are discrete, 1, 2, 3, 4, or 5, we say number. And in the same vein, we don't say less, all right, when we can count them. We say fewer. Right. In other words, when they are whole number values. We would talk about less tea in a cup or less water in a dam. Those are continuous quantities. But we would talk about fewer runs, fewer children, fewer animals, whatever it might be. Right. So just to for the English piece of this, here discrete we would talk about fewer, but continuous we would talk about less. All right. We would, in similar vein, we would talk about the number versus the amount. And here we'd be talking about many versus much. How much water is in the cup? How many children do you have? Not how much children do we have. Okay? Right. Onto probability distributions, and this is really the balance of this whole topic is about probability distributions. What a probability distribution is, it's just the way that the probabilities are distributed or shared across the possible outcomes. Okay, we're going to consider discrete ones, all right, and the discrete ones are actually called probability mass functions. Bit of a weird name, and you don't really need to worry about it too much. Probability mass functions. And we're also going to talk about continuous ones, which are called probability density functions. Okay. Right. A defining characteristic of every single probability distribution is that the sum of all the possible outcomes must be 1. Every probability distribution. Okay, so let's consider a very simple example, and this one's a discrete one. When I throw a die, there are 6 possible outcomes. Each of them's got the same probability of 1/6. Okay, and so the 6 possible outcomes probabilities add up to 1. We can write this probability distribution like this, and this is an important sort of notational thing. It's a little bit confusing. The big X stands for sort of the value on the dice, and the little x stands for the specific values. Okay, so the probability that the value on the dice is equal to 1, 2, 3, 4, 5, or 6 is 1/6. Every other possible value for x has a probability of 0. In other words, we can't get a 7, we can't get a 2.5 or a 3 1/8. Okay, right. So we could write this, the x, but we always use the capital letter and the little letter. Okay. So the big X represents the sort of the thing, and the little x, the values it can assume. So here, this would be exactly the same. This time we've used R. The probability the big R can take on the values of little r are 1/6 for 1, 2, 3, 4, 5, and 6, and 0 elsewhere. Okay, and they add up to 1, and they always will. All right, we could graph this. All right, this is the probability of x on the horizontal axis, and this is x on the probability of x on the vertical axis, and the values of x on the horizontal axis. These are about 16 2/3% each, and they add up to 100%. Okay, let's look at another example. So here's the sort of probability distribution when I go fishing. The probability that I catch no fish, 20%, 1 fish, X%, 2 fish, etc. Right, the first thing is determine X. Well, what we're going to use here is we're going to use that the sum of these probabilities is 100%, okay? And quite quickly we can realize that X is actually 15%. The next thing says, what's the probability that I'll catch at least 1 fish on a given day? Now, if we want to include at least 1 fish, basically the little trick here is that we actually want to include that, which is we now know is 15%. We want to include that, we want to include that, we want to include that. All right. So in fact, the easiest way of working it out is not to add all of those up, But to actually take the complement, the balance of the complement of at least one is none. So the probability of at least one fish catching at least one will be 1 minus the probability of no fish. So in fact, it will be 1 minus 20%. Remember, 1 is 100%, so in fact, it will be 80%. Okay, right. Here's another example. This time we're not told what we're sort of dealing with, but we've got different values of x, and we've got the probabilities that they occur. And we are asked to find the value of p. Now, what we know, because it's a probability distribution, is that all these values must add up to 1. Now, if we add up the p squareds, they're actually 6p squared minus p squared. There's 5p squareds. Right? In terms of the p's, there's 2p here, a p here, and a p here. They're actually 4 p's. All right? And this must add up to 1. Right, so now if we solve this quadratic equation, 5p squared plus 4p minus 1 equals 0. Right, it's just a standard quadratic equation, the likes of which are being solved all the time in core maths at the moment. This is going to be a plus 1, and in fact, this is going to be a minus 1. So we end up with p equals a fifth, or p equals minus 1. Right, now p can't be minus 1. If we look here, we can't have a probability of minus 1. So we're going to scratch that answer, and in fact, p is a fifth. So now we could work out the probabilities of each of these things. So this, in fact, is a fifth. It's 20%, all right, and we could work them all out. The next and last thing we've been asked to work out is what's the probability that our x is bigger than 2? Bigger than 2 means either 3 or 4, right? And if we work out these probabilities, okay, this one will in fact be p squared is a 25th, so this will be 4 25ths. And in fact, this one is also 4 25ths. It's actually a fifth minus a 25th. All right, and remember, sorry, it's not 4 25ths. A fifth is 520, yeah, it is 4 25ths. Okay, so in fact, the probability that x is bigger than 2 is actually equal to 8 25ths, or 32%. 32 out of 100, 8 out of 25, 32 out of 100. Okay, right, now we're going to look at two special discrete probability distributions. The first one's called the hypergeometric distribution. Don't freak out at the name. It's actually much simpler than it might seem. Right, so what we've got here now is we've got a bag that contains 3 red beads and 7 green beads. We're going to withdraw 5, okay? And we could, that's either one at a time or all at once. Doesn't make any difference, but we're not putting them back. That's an important thing. All right. The probability that we get 2 red beads and 3 green beads. Well, let's just remember our formula for probability. The probability of something happening is the number of ways it can happen over the number of things that can happen altogether. So this denominator here is actually the number of ways that I can choose 5 things, 5 beads, from the 10 that are in the container. 5 from 10. And we know the answer to that. That is actually just 10 combination 5. So that's what's on the denominator of our fraction. With a blue pen, I'm going to look at the numerator now. All right. Now, how many ways can I choose 2 red beads from 3 red beads? Okay. And the number of ways I can choose red beads, all right, is actually going to be 3 choose 2. Right, I just want 2 of the 3. The number of ways, so this is for red beads. And then I want to get 3 green beads. But there are 7 green beads. So this will be 7 combination 3. That's the number of ways I can choose the green beads. Right? And each choice of red beads can go with each choice of green beads. So the numerator on this fraction here is actually going to be 3/2 multiplied by 7/3, and that will give us our overall final probability. Okay, let's just bring up a calculator and see what that looks like. Okay, so let's put in a fraction here. Just be aware that when you go 3 combination 2, you need to use a multiplication sign here between the next one. 7 combination 3. All right, and on the bottom here, we're going to have 10 combination 5. And we get 5/12. And that's the answer. Okay, just a little thing that I want to draw your attention to, which will always be the case here. If you add those two numbers up, you get this number. And likewise, if you add these two numbers up at the bottom, you get this number at the bottom, always. Okay, all right, so there it is. The next question has actually got a typo in because it's actually exactly the same question. This is meant to say now 2 green beads and 3 red beads. Well, basically, I want the number of ways I can choose 2 green beads from 7, multiplied by the number of ways I can choose 3 red beads from 3 red beads, over the number of ways I can choose 5 beads from 10 beads. Okay, and once again, just a reminder that these top numbers add to that, and these bottom numbers right, and I can work this probability out. Let's just quickly do that. All right, given that I've got that calculation on my calculator, I can probably just go and sort of fix this. We now want 3 from 3 and 2 from 7, still 10, 5, and I get 1/12. Okay, the next one, the probability of at least 1 red bead. Okay, now at least 1 red bead, I need to think about the best way of doing that is going to be 1 minus the probability of no red beads. 0 red beads. Okay, and if we think about it, that will be getting 0 red beads from 3 red beads, getting all 5 green beads, all 5 beads must be green, okay, from 7, and this is over, remember, add and add, this is over the number of ways I can choose 5 beads from 10 beads. Okay, this is the probability of no red beads, so at least 1 red bead will be 1 minus that. All right, and we actually get, I think we get 11/12, if my memory serves me correct. I hope I've got that correct, I think so. Okay, more red beads than green beads. Well, now here we would have to sort of think about some options. Remember, we're drawing 5 beads, so we would need maybe 3 reds and 2 greens, or 4 reds and 1 green, all right, or 5 reds and no greens. Theoretically, those are the possibilities, but in fact, there are only 3 reds. So this one is not possible, and nor is this one. Okay, so we've actually already worked this out. 3 reds and 2 greens was actually this answer over here, 1/12. Okay, right, let's do another example. Suppose there are 3 oranges, 4 pears, and 5 apples in my fruit basket. I randomly choose and eat one each day for 3 days. Okay, what's the probability that I'll eat one of each type of fruit? Well, basically, the number of ways I can choose 3 bits of fruit from 7, 12 bits of fruit. That's the total number of ways I can randomly choose 3 from 12. But I now want to make sure that one of those is an orange, and the number of ways I can choose the oranges is 3. It's 3 choose 1, which happens to be 3. The number of ways I can choose the pears is 4. It's 4 choose 1, which is 4. And the number of ways I can choose the apples is 5 choose 1, it's 5. Okay, remember what I said earlier? If we add these numbers here, they add up to this number. And if we add these numbers here, they add up to the number at the bottom. Okay, so there it is. And I can work this out, okay? Final answer here will be, this is just 3 times 4 times 5. I'm just going to do that in my head. It's actually 60 over 12 combination 3. So, in fact, what I'm going to get is let's just work out what 12 combination 3 is. 12 combination 3, it's 60 over 220. Right, if we do that on our calculator, we'll get a kind of simplified version of that, but 60 divided 220. Right, it's 3/11. If we wanted it as a decimal, as a percentage, we could have 27.3%. All right. Don't stress about the format of the answer. We'll tell you what format to put it in. Okay. What's the probability that I eat exactly 2 apples? Right. Now, what I want here is I want 2 apples out of the 5 apples. Remember, I'm eating 3 pieces of fruit. So now I want 1 other piece of fruit, and I don't care whether it's an orange or a pear. All right. There are 7 of those things. Okay. And remember what I said, the top numbers and the bottom numbers. This will be 12, 3. And in fact, this will be 12, 3 for this entire question. Okay. All right. Another option here is to work out, although it's longer, is to work out the probability of 2 apples and a pear, and then we would add 2 apples and an orange. Okay, so let's just quickly have a look at this. This is going to be, in terms of our answer, it's going to be 5 choose 2. I happen to know that that's 10 and that that's 7. So in fact, the answer is going to be 70 over 12 combination 3. 12 combination 3. Right, and I get 7 out of 22. Okay, what's the probability that I eat 2 apples and an orange? Well, 2 apples from 5, 1 orange from 3, and if we like, we can put 0 pears from 4. Okay, this number here is actually just 1, so it doesn't affect anything. But remember, if we're adding we must definitely have 12, 3 on the bottom. So in a way, putting that 4, 0 there is actually useful. All right, and there's going to be our answer. Okay, this on the top, I know that 5 choose 2, I happen to know is 10. All right, 3 choose 1 is 3, and 4 choose 0 is 1. So I've got 30 on the top. And on the bottom, I've got 12 combination 3. And I get 3 out of 22. 3 out of 22. Okay. Now, the last thing we're going to do today is we're going to write down the probability distribution for the number of oranges. Remember what the format of this is. We're going to write down probability, and we're going to use a big letter. Let's use big X equals little x. Okay. Now I'm eating 3 pieces of fruit. Remember, this whole question talked about eating 3 pieces of fruit. So basically, the number of oranges that I could have in the 3 days, I could have 0 or 1 or 2 or 3. All right. Now I need to put a formula in here that I'm going to use to calculate the probability of each of these things. Now remember, we're talking about oranges, all right, and there are in fact 3 oranges. So of the 3 oranges, I want to have x of them being oranges. Now I'm eating 3 pieces of fruit, so if x of them are oranges, then 3 minus x must not be oranges. Okay, and those non-oranges can either be apples or pears, of which there are a total of 9 apples and pears. So this would be 9. Now remember, the denominator, if we add the tops, we get 12. If we add the bottoms, we get 3. This whole question has had the same denominator every time, 12, 3. This little formula here will give us the probability for any value of x from 0, 1, 2, or 3. In other words, we can work out how the probabilities are distributed, how they're shared, all right? The probability distribution for this particular situation. Okay, what we mustn't forget to write is 0 elsewhere. Right, so every other value of x, because I'm only eating 3 pieces of fruit, the probability of having 5 oranges or 4 oranges is 0. The probability of having 1.5 oranges is 0. Okay, right, we look forward to carrying on tomorrow. Tomorrow we're going to look at another example, and we're actually going to look at the formula that one gets given, although to be honest, the formula is horribly confusing and not very helpful.